Is the video for the last section of notes for Unit 6. So in 6.3, we're going to be talking all about what are called residuals. Basically, if you remember what we've talked about so far, in 6.1 we talked about scatter plots, kind of describing scatter plots and how that works. 6.2 we spent trying to find a line of best fit that would go through the data as best as possible. And in 6.3, residuals are going to be a way for us to measure how effective our line of best fit is at predicting the values for the data. So residual is the difference between the observed value of the response variable and the value that's predicted by the regression line. So in other words, you're looking at how far off was your prediction from what actually happened. So to calculate a residual, you're going to take the observed value minus the expected value, or another way to think about that is taking y minus y hat. Now, when we interpret a residual, we're going to say a negative residual is an overestimate, because if it was negative, that means that you overpredicted how much was in there. Whereas a positive residual is going to be an underestimate. In other words, you were a little bit lower than what it should have been. So to do a practice problem with this, let's go ahead and calculate and interpret a residual for a can of soda from 6.2 that was tapped 4 seconds and had 260 milliliters of soda left in the can. So thinking back to that example where we're talking about tapping the can of soda that we talked about in 6.2, I've gone ahead and copied down the regression equation that we were using. So we need to first kind of label all of our information that we were given. So the 4 seconds, that's our input, that's our x value. The 260 milliliters, that's the actual observed value, so that's going to be y. So really what we need to find if we want to find this residual is we want to find what y hat would be. So y hat, we have an equation for that, is equal to 248.6 plus 2.63 multiplied by x. So let's go ahead and plug in what x was equal to. So that would be plugging in a 4. And then we'll go ahead and simplify that. Go ahead and type it into your calculator. 248.6 plus 2.63 multiplied by 4. And that's going to be 259.12. It's actually a pretty close estimate if you think about it. Our line of best fit is predicting that can of soda should have 259 milliliters in it, and it actually had 260 milliliters. So we were just a little bit lower than what we expected. So actually a really close estimate. But let's go ahead and see how close. So our residual is going to be equal to taking our observed minus expected, or y minus y hat. So that would be 260 for y minus 259.12 for y hat. So we'll go ahead and type that into our calculator. 260 minus that 259.12. And that's going to be 0.88 for our residual. Now, as we go to interpret this, 0.88 is a positive number, so a positive residual is an underestimate, which we already knew because 259 was a little bit less than 260. So what we're going to say as our interpretation is that we underestimated the amount of soda remaining by that 0.88 milliliters. So residuals will actually include the label for our response variables. Unlike where R, we don't include that. With residuals, we will go ahead and include a label for that value. Okay, so let's take a look at an example here. We're going to talk about McDonald's beef sandwiches. So I've got some information on those. I've got both the amount of carbs in grams and the amount of fat in grams. So we first need to decide which is going to be our explanatory, which is going to be our response. And so I would say that the amount of carbs is going to be our explanatory, whereas the amount of fat is going to be our response variable. So for part A, how can we determine the best regression line for a set of data? In order to do that, we're going to compare the R squared values for different models. And again, the ones that we are mostly going to focus on are going to be the linear model, which we're most familiar with, the quadratic model, which we haven't used yet, as well as the exponential model, and we're going to look at the r-squared values for each of those. So let's go ahead and do that. Let's maybe see which one would be better to use. So we're going to put all that information into our stat menu. So stat, choose edit, put all of your carb information in list 1, and all of your fat information into list 2. Once you've done that, we're going to go ahead and close out of that screen, so second mode, and then we'll go ahead and go back into the stat menu, and let's go ahead and do linear regression first. So we'll go down to option 8. And really, we're only interested in one thing. So once we're done with list 1, list 2, we're not going to even bother with storing the regression equation. We're just going to hit calculate, and we're going to write down what the r-squared value is. We're not even going to write down the line of best fit for right now. We'll go back and do that later on if we need to. But for linear regression, our r-squared value to 2 decimals is 0.55. Now remember, the closer to 1, the better. So this one, not real great. It's kind of halfway between 0 and 1, but not very close to the number 1. So let's maybe try a quadratic regression next. So we're going to go back to stat, over to calc, and this time we're going to choose option 5 for quadratic regression. Now all the options are going to stay the same. We're going to leave list 1 and list 2 in there. We're going to go ahead and hit calculate. And this time for quadratic, our r-squared value is 0.68. So hey, still not great, but a little bit better. In this case, 0.68 would be our r-squared value. And then our line of best fit obviously is going to be a quadratic equation. So instead of just having regular old x, now we've got ax squared plus bx plus c, and then you would have 3 numbers to plug in there instead. But let's go ahead and try one more. We're going to go stat, over to calc, and obviously there's more that we could try. Like there's cubic regressions, quartic regressions, there's natural logarithmic regressions, there's power regressions, all sorts of different things you can do. I'm just showing you the 3 most common, which are linear, quadratic, and the one that we're choosing right now, which is exponential. So with exponential regression, again, everything in there is going to stay the same. And we're going to just write down what our r-squared value is, which would be 0.62. And at this point, we would make a decision on which one is best to use. And in this case, quadratic is closest to 1. And so that would probably be our best fit for the data. Now, obviously, we're not going to spend too much time talking about quadratic and exponential, so we are going to continue to use the linear regression, so we'll go back and recalculate that in just a moment. But if we had more time, we would probably spend a little bit of it talking about how to use a quadratic regression or an exponential regression in a similar way to a linear regression equation. But just so that you're aware, in case you ever wanted to know what the best regression was, you kind of have to try a few of them and figure out based on their r-squared values which one is the best. All right, so for part B is the least squares regression equation resistant to outliers. This is something we actually talked about in 6.2. The answer to that is no. Obviously, if there are outliers, it's not going to be resistant. So let's go ahead and calculate the equation of the least squares regression line using our calculator. Make sure to define our variables, and we're going to sketch a scatter plot with a graph of the least squares regression line. Now again, while quadratic was the best fit, just to keep things simple, we're going to keep it as linear. So let's go back into stat. We're going to choose calc. We're going to redo that linear regression, and we'll go ahead and store the regression equation as well. So we're going to choose option 8 for linear regression. Again, we've got list 1 and list 2 already in there. For store regression equation, we want that to be our y1. So we're going to go to our vars menu, over to yvars, option 1 for function, option 1 for y1. That way, when we're done running our regression, it'll already have that in our graph as y1. And then we'll go ahead and hit calculate. And let's go ahead and write down what our regression equation is. So we would say that y is equal to, or y hat is equal to, let me be a little bit more careful, negative 40.20 plus 1.71 multiplied by x. Now again, we can define our variables in a couple different ways. We can just write out that y hat is the predicted amount of fat in this case, the predicted fat, and x is the number of carbs in grams. Or you could go ahead and just write those into your equation as fat hat is equal to negative 40.20 plus 1.71 multiplied by carbs. All right. In addition, let's go ahead and write down both our R and our R squared value. So R is just 0.743. So it is somewhat close to 1. So we would say that it's got moderate strength and that it's got a positive association since it's a positive value. For R squared, our line of best fit isn't the greatest, but it's still not too bad. 0.553. So we would say that the line of best fit kind of does a decent enough job of predicting our data. All right, so now let's go ahead and draw in our scatter plot along with our line of best fit. We already know that X is going to be the amount of carbs, and again, that was in terms of grams, and that the Y value is going to be the amount of fat in grams. All right, so let's let the calculator do the work for us. We're first going to go to Y equals and make sure that our equation is in there. Again, the nice part about storing it the way we did is that you get all of the decimals, not just some of them. Also, plot 1 is turned on, but let's go ahead and make sure that that all looks good. So let's go second Y equals to our stat plots. Plot 1 is in fact turned on. Type is scatter plot, list 1, list 2. All of that looks good. We're now ready to press zoom and choose option 9 for zoom stat. And we should be able to see our data for our line of best fit as well as all of the actual data itself. So just to draw a rough sketch of that, our line of best fit obviously going in a positive direction, looking something kind of like this. We've got our first couple of points below our line of best fit. Our next couple are above, and we alternate just a little bit there until we get out to our last couple of data points. All right, so again, not perfect, but at least a semi-decent sketch of what the data would look like. Don't forget to go to your window to include the numerical labels as well. So our X values were going from 29.6 to 46.4, and our Y values were going from 3.39 up to 47.61. Okay. So now let's go ahead and use that information to do a couple of things with it. Let's first interpret the slope and y-intercept in context. Let's go ahead and start with slope. Our slope of our regression line was 1.71. So for each 1 gram increase in our explanatory, so for each 1 gram increase in carbs, we would expect the fat in grams to increase by about 1.71, yep, so 1.71 grams. Next, we'll go ahead and do y-intercept. So y-intercept, remember, is your constant, so negative 40.2. So again, that would be 0, negative 40.2 as a point. So we would say a sandwich with 0 grams of carbs would have negative 40.2 grams of fat. So in this case, the y-intercept doesn't make a whole lot of sense, and oftentimes it won't. That's okay. We can still interpret it. Just know that the interpretation in context is not going to make a whole lot of sense because obviously you can't have negative 40 grams of fat. But in E, let's go ahead and talk about the residuals. So this is our chance to practice once again calculating a residual. So just as a reminder, when we do that, we've got our 45 grams of carbs is our X value, and then 29 grams of fat is our Y value. Now, to find our Y hat value, remember here's our regression equation, again was negative 40.2 plus 1.71 multiplied by X. So let's go ahead and plug in X to see what our Y hat value is. So negative 40.20 plus 1.71 multiplied by 45. So when we put that in, that'll give us our y hat value. So let's go ahead and do that on our calculator. So we'll close out of everything we had. Negative 40.2 plus 1.71 multiplied by 45. Let me go back and fix that. It should have been 1.71 instead of 1.7. Maybe. Okay, well, I'll just go ahead and do it off to the side here. Let me grab a different calculator real quick. So negative 40.2 plus 1.71 multiplied by 45, and that's going to be 36.75. So we predicted it would have quite a bit more fat than what it actually had. In this case, 36.75 is positive, so that would be, well, that's over our 20 grams of fat that we had. Let's go ahead and find the residual so we can interpret it. So our residual, we're going to take our observed minus expected, or y minus y hat. Y is the 20 grams of fat that we had, or 29 grams. Let me go ahead and rewrite that a little bit better so that I can actually see it here. There we go. So 29 grams of fat minus our predicted 36.75, and that's going to be a negative 7.75. So a negative residual means that we over-predicted it, which we already knew because obviously 36.75 is more than 29. So what we would say is that we overestimated the amount of fat in grams by 7.75 grams. Now, the reason for that, for those that do not eat at McDonald's very often, may not be familiar with the Big Mac, but the Big Mac is somewhat different from the other sandwiches on the menu because in addition to the top bun and the bottom bun, there's actually a bun in the middle of the sandwich as well. So that adds additional carbs, whereas the amount of meat in the sandwich would stay the same. So it still just has two patties, but has an extra bun in the middle. So that would be probably the reason why it was an over prediction or an overestimate, was because of the fact that you have more carbs than fat for that sandwich. Okay, so the last thing to share with you guys is this idea of a residual plot. I'm going to talk about that while I'm restarting the calculator real quick here. So a residual plot is a scatter plot of the residuals against the explanatory variable. In other words, you look at all of the residuals for every single data point. We've only looked at it for one in each case, but you look at it for all of the data and graph it all together. As we have to force quit out of that. Here we go. Cool. And then let's go ahead and reopen it. All right. So the purpose of a residual plot, why are we talking about it in the first place, is that it helps us to decide if a linear model is going to be appropriate or not. So we can use a residual plot to decide if a linear model would fit the data or if it's not quite appropriate. Now, how can you tell if a linear model is appropriate? Well, we can tell that a linear model is appropriate if there's no pattern which is visible in the residual plot. So let's go ahead and do that for our McDonald's data. Before we do that, let's just make sure, because mine went away when I quit, that you've done a linear regression recently using that data. So if you have not already, if you've just been following along, make sure that you've done your regression for that McDonald's data first, because your calculator has to have that regression calculated before it can do the residual plot for you. Okay, so here that is once again. What we're going to do is we're first going to go to y equals and clear out anything that's in there. So that's done. Then we'll go into our stat plot menu, and we're going to change one thing about plot 1. So for right now, plot 1 should still be turned on. You should still have your type as scatter plot, and it should say list 1 as x list, list 2 as y list. We're going to actually change our y list to being something different. So instead of list 2, we're going to make this all of the residuals for our data. In order to do that, you're going to use second stat to get to this list menu. So above stat is this list option. So you'll see this is where you could choose any of the different lists, list 1, 2, 3, 4, 5, and 6. And then down at the bottom of this menu, there should be another option as well called resid. And no surprise there, that's going to be our residuals. So for me, it's all the way down at the very bottom, past some other stuff, and we're going to choose that resid option. If you don't see resid as an option, then you probably have not done the linear regression yet. So make sure you do the linear regression first, and that way you can get the residuals. Once you've done that, we're going to go back to Zoom, choose option 9 for Zoom Stat, and your data should look something kind of like this. So for our residual plot, we're going to go ahead and just sketch what that looks like, and then we'll do our interpretation of that. So we've got a couple points that were below, so these would have been underestimates, and then above, and then so on, looking something kind of like this. And I would say that there is no pattern to the data, so a linear model would be appropriate. What you want to watch out for is if you were to do a residual plot and it looks something maybe kind of like this, where pretty clearly there's kind of a pattern there, the points are kind of following something, then this would not be appropriate. This would not work for a linear set of data. But for our model, again, I really don't see a pattern developing, and it looks like about half the points are above and about half are below. You really can't ask for much more than that. I would say that we're good to go. All right, guys, so that wraps up our section of notes. That wraps up also our Unit 6 of notes, looking at how residuals worked and how well did our line of best fit predict our data. That being said, until next time, guys, have a great rest of your day.